ask, yes. But if we're at 101, I think we're okay.
All right, whenever you think is best then.
Aaron, go ahead and push record.
All right, hi everyone, welcome to our October webinar. I'll make this brief to give more time to our panelists. My name is Lily Horn and I am a co-PI for the Regional Induced Seismicity Collaborative, which is a consortium made up of researchers from several state geological surveys across the southern mid-continent of the US. RISC was created to address regional issues that extend across state borders and jurisdictions. In addition to conducting research, one of our goals is to put on a bi-monthly webinar series with content that appeals to the scientific community, educators, industry members, regulators, and members of the public. As this webinar series has evolved, we've started adding panel discussions to engage both panelists and audience members. And today's panel is discussing the state of induced seismicity within each of the panelists' respective region. This discussion is moderated by Dr. Paul Ogwari, a geophysicist at the Oklahoma Geological Survey. Thanks again, everyone, for being here. And with that, Paul, please take it away.
Thank you, everyone, for joining us today. In today's discussion, we're going to have 4 panelists. We're going to have panelists who are seismic network managers within the region. So we're going to have a brief introduction, after which we are going to have questions, and we would welcome any questions from the audience. Today, we're going to discuss about the state of seismicity within the region and what the managers for each network are preparing for future challenges of seismicity within the region. So to start with, let's have Mitch with us, and then Jake, and then Alexandros, and then crown with Emily with your introduction. So Mitch, you can take over.
Thank you, Paul. Thank you, Lily. Let's see if I can share my desktop. Or how about if we share that window instead? Can you see that okay?
We see the note.
Yep.
Perfect.
Hey, my name is Mitch Withers. I'm a research associate professor at the University of Memphis, and I'm the network manager there. This is a map of the stations that we use. There are 2 polygons outlined in black. The country is divided up into various authoritative polygons, and those polygons are combined together into a national system. There's a lot more I could say about that, but not in 5 minutes. But the stations are, the symbol depicts the different types of sensors that we have, and the colors represent the different organizations that operate stations within our 2 authoritative polygons. The red stations are the stations operated by CERI at the University of Memphis that I'm in charge of, but we also rely on many other partners within the region to contribute data to our efforts to locate earthquakes within these 2 polygons. And those are the Arkansas Geological Survey stations are over here in Arkansas in green, and St. Louis University stations. Bob Herman has retired, and we're in the process of transitioning those. And we get data from our partners at the University of Kentucky here in green, and the University of South Carolina in yellow. And then all these blue stations are the USGS stations that I'm sure Emily will have more to say about later. Now, the underlay here is the USGS National Seismic Hazard Map. Our monitoring, of course, focuses on the 2 seismic zones primarily responsible for the hazards in Tennessee. They are the New Madrid seismic zone here in the west and the East Tennessee seismic zone in the east. We're also concerned about or pay attention to the Charleston seismic zone down here in South Carolina, as well as the Wabash Valley seismic zone up here in southern Indiana, and the Central Virginia seismic zone where the Mineral Virginia earthquake was in 2011. This is a map of seismicity in our catalog. It began in 1974 with St. Louis, and then CERI joined in the mid-'80s. And they're surprisingly, it shows the different seismic zones that I was talking about earlier here in New Madrid in the west, and there's a significant amount of seismicity in north central Arkansas. A lot of this blue cluster is our sole example of induced seismicity in this part of the country. And you can see the East Tennessee seismic zone, and there is a tight cluster down here in Somerville, just northwest of Charleston. And surprisingly, all the larger earthquakes in this catalog, greater than 5, are not in the areas with the most seismicity. So that in itself is a lesson about earthquakes in the east, in the stable continent. And this is just a similar map, only for just 1 year of earthquakes, so to show that it is a fairly stable pattern where these seismic zones are highlighted, as well as the north central part of Arkansas. And again, another significant event up here in central Indiana where we don't expect it, but we do have to be prepared for it. If I would have shown this map from a year ago, the prior year, there would be 4 events rather, that were greater than 3.5. And there's a cluster here that are some remaining aftershocks from the magnitude 5.2 Sparta earthquake from August of 2020. And this is a histogram of seismicity. I began this histogram in 1995 instead of 1974 because I have digital waveforms for every event on this list starting in 1995. And you can see in this plot that seismicity varies depending on the evolution of the seismic network, which is not a static thing, as well as various episodes of different seismicity. The one that stands out the most is the Guy Greenbrier swarm, which was an induced seismicity swarm in central Arkansas. And this is also the time when the Arkansas Geological Survey installed their state network. They contract with the University of Memphis to operate the network. And so that also has something to do with the increase in seismicity here after 2011, because we're doing a better job in Arkansas. And then you can see the N4 network, which were the majority of those blue stations, became active in 2013 and 2014. Those are operated by the USGS, but it also helps us do a much better job of processing seismicity throughout the broad entire region. And then you can see the aftershocks here. The blue bars here are for the NM polygon on the west, and the orange or red are for the eastern polygon that we refer to as the SE for southeast. And you can see the aftershocks from the Sparta earthquake in 2020 really ramping up into eastern Tennessee. But otherwise, it more or less remains stable if you account for the various swarms and aftershocks and network evolution. And some of our primary challenges in the future, we still have some fairly old technology that uses analog telemetry. We're working, and most of it is isolated in the New Madrid seismic zone. We're working, because that's where we have most of the stations. We're working on upgrading that from analog to digital telemetry. And we also want to be prepared for early warning. The earthquake early warning is active and in production on the west coast of the United States, but nowhere else. It's really not feasible to do it over broad swaths of the country, but for various targets of special interest like New Madrid or East Tennessee or even Oklahoma, it would make sense to have a regional earthquake early warning for events, large events that occur within specific regions, not necessarily the whole country. My statement earlier about where the magnitude 5s are notwithstanding. And of course, it's a perennial issue of funding for seismic networks that we all have to pay attention to, because it comes and goes. I see there's a chat, but that's not a question. So that's all I have for my brief intro. I'll pass it back to Paul unless there are questions.
Yeah, I think Jack can take over first.
All right, just bear with me as we make the transition here. All right, well, thanks for the invite. I'm honored to be in the company of these panelists, and you know, we us, you know, scientists and technologists, we like to, you know, get impressed by our doodads and our gizmos, but we also have to acknowledge the sort of sweat equity that goes into building up these networks. It's not just the digital waveforms that come out, but the careful, you know, installation, maintenance, planning, and other work that goes into it. So Oklahoma, as many of you are probably aware, has been quite seismically active in the last decade, but there's also a long history of some tectonic influence that's produced this induced seismicity that we've observed in the last decade. So there's been a long, rich history of earthquakes almost anywhere across the state, and most recently associated with oil and gas activities. And so on the right-hand side, we have some damage from that 2011 Prague earthquake, which you can see also mapped on the top there. So we now understand that a lot of that seismicity in the recent past is attributed to wastewater disposal that was realized on a broad regional scale with the advent of hydraulic fracturing also being sort of widely used across north central Oklahoma. The particular play that they were going after, the shales actually included significant volumes of produced water. So this is water that is, was locked up with the hydrocarbons, and thus the cheapest, easiest way to, and most environmentally sound way to get rid of that water is to pump it deep underground. And so in Oklahoma, the formation, the Ordovician limestone that exists right above the sort of basement is called the Arbuckle group of rocks. And so if we track the Arbuckle volumes statewide that were disposed into injection wells, we can see that climb of Arbuckle volumes actually anticipated that increase in the seismicity rates in Oklahoma. And during this period from about 2014 through 2017, the seismicity rate in Oklahoma outpaced the seismicity rate in California. So while the OGS has a long history, several decades long, of monitoring seismicity and operating seismographs across the state, over the decade, we've had to build up the sort of digital network in a very ad hoc sense. So my predecessors, were able to get, small chunks of money that were invested into the network. We're able to borrow a significant amount of instruments over the years from the IRIS Pascal pool and telemeter those instruments and operate our network. Of course, we do all this sort of the scientific product creation in-house, and then we push those solutions to USGS. Prior to May 2019, that pushing those solutions to NEIC occurred, and NEIC would be able to choose whether they wanted to use their own location or one coming from us. Now, we certified our network with USGS and became a self-supporting part of the ANSS network. So we have our own polygon that Mitch referred to that encompasses the state of Oklahoma. So when solutions are coming from USGS,
We lost your sound, Jake.
so when solutions are coming from USGS, they're being created by OGS. So in addition to sort of boosting up the engineering aspect of adding more stations, building better stations, siting in less noisy environments, if necessary, we've also tried to make some improvements in the way in which we process the waveform data coming into us. So we developed a Python package called EasyQuake in-house that we use to actually identify earthquakes that would have been otherwise missed. And that entails using some of the machine learning pickers that are available. We have the choice of the EQ transformer picker out of Stanford or the GPD picker that was developed at Caltech. And this software program actually does the full turnkey ingesting of continuous waveforms and will produce an earthquake catalog. So we published a paper that software is open source and out there and available. And this is just an example of how we improve our detection. We're able to detect about a factor of 2 more earthquakes than we were previously via our sort of near real-time detector. And here's just a quick example of an earthquake that would have been otherwise undetected, very small magnitude, 0.7. But it's important, I think, to sort of fill out these catalogs and provide the best sort of solutions that we can and understand the seismicity as it unfolds. And so here's an example. While the earthquakes are down significantly across the state, in the last month, we still see significant activity stretching both across from north border to south border and west border to east border. And we also published a paper sort of describing the evolution and how that network has been built up over the last decade. That was published in a special volume of SRL along with a number of other sort of networks. So that's all I have.
All right, Alexandros, take over.
Okay. Oops. Where is my, here it is, share screen. Okay, can you see my screen?
Yes, looks good.
Okay, thanks. So I would like to thank also the Paul and Lily for inviting me to participate in this panel discussion. My name is Alexandros Savvaidis. I'm the manager and PI of TextNet, the network manager of the network, and I'm also leading the seismology team here at the Bureau. I joined the Bureau back in January 2016. Actually started TextNet because at that time there were no statewide network for the state of Texas. TextNet has been authoritative a couple of years ago, and now whatever you see on the USGS website is also coming out from our analysts. And this is a screenshot of the recent event that happened earlier today in the border with New Mexico. My presentation includes the information about the network, some monitoring tools we developed, and then seismicity overview for the state of Texas. So when I first presented TextNet in April 2016 in SSA, the plan was to, of course, add complementary to the existing stations that were like 18 stations at that time, more permanent stations, in order to make sure we have an evenly grid space network that can help us understand the seismicity in the state. Of course, additional to that, we added a lot of portable stations, and we came up to now to have more than 150 real-time stations. So we moved from 18 stations to 150 real-time stations in a period of like 4 years. Most of the stations are deployed in areas where we have seismicity that is in the southern part of Texas, in DFW, in the Permian Basin, and also in the Panhandle of Texas. We have an earthquake catalog that you can, of course, connect and get the information about the seismicity. There is an API that you can directly get the data to your GIS system. We provide a video of seismicity with time, so you define the time period of the step time period for the video, and then you can see how the seismicity evolves with time and space for the state or a specific area of region. We update quarterly our maps with the information about our depth uncertainty and also the magnitude of completeness that we have from the reported data. We have developed also different monitoring tools. One of the tools is with a collaboration with the industry and the Royal Commission, because some of the private array data that are available to us, we have to provide information to the regulator about the availability of data. Now, our seismological setting for magnitude 3 and above earthquake seismicity in Texas is during the period of 1975 and onwards, as you can see on the left-hand side, shows that there is increase in seismicity for the state of Texas for the last 20 years. Actually, most of what we have is a high increase from 2009 and onwards, where we have 3 main areas. One in the southern part of the state, in the Eagle Ford area, where it seems the recent seismicity is caused by hydraulic fracturing. We have seen also seismicity in the Dallas-Fort Worth region, where it seems the seismicity is caused by injection. And also the most recent high seismicity rate we have in the state is in the Permian Basin. We have 3 areas of high seismicity and actually different type of causal factors of earthquake activity. Getting into more historical information about the seismicity, here you see the magnitude 4 and above earthquakes in the Permian Basin. The blue region specifies the earthquakes that happened between 1931 and 2016. There are like 4 earthquakes with magnitude 4 and above. But if you go to September 2021, you will see there is a high increase of seismicity. We had a lot of earthquakes with magnitude 4 and above, including the border with New Mexico. And actually moving more detail about this region, you can see that here we had a high increase of seismicity for the last month. Actually, during September 2021, we had 5 earthquakes with magnitude 4 and above. This is an area of high interest, of course. And another area that's of high interest is the Midland Basin, where we had up to now only 1 earthquake of magnitude 4 and above. But we had a lot of earthquakes with 3.5 and above. And in that case, the most recent one happened in September, last September. And we have seen a lot of interest from the public about this earthquake, of course, since it is very close to the city of Midland. And we had a lot of field reports due to this earthquake. So that's all from my side. Thanks for the invitation again. And let's move to Emily.
All right, let me go ahead and get my screen shared here. All right, can everyone see my slides?
Yes.
Wonderful. All right, thanks so much. Good afternoon, everyone. Thank you for the invitation to join this discussion today. My name is Emily Wolin. I am the Seismic Network Manager at the USGS Albuquerque Seismo Lab. And I've been in this position for about 2.5 years. So still learning a lot and whipping these networks into shape here. So like I said, I'm at the USGS ASL, and our mission is to support the operation of seismic networks for monitoring and research. So at our facility down in Albuquerque, we test and evaluate seismic equipment. We do a lot of quality control on data and metadata, and we support seismic station operations. Our actual earthquake location, our goal at ASL essentially is to feed data into the National Earthquake Information Center in Golden, Colorado. That's where our analysts are located that detect and characterize earthquakes. So down at the ASL, we're more focused on operating the networks and supporting the flow of data up to Golden, the folks who locate the earthquakes. Our facility is located just at the edge of Kirtland Air Force Base on land owned by the Pueblo of Isleta. And we have a number of facilities for testing and evaluating seismic equipment. A couple of tunnels bored into the granite mountains here that you can see in the background, a number of boreholes and post holes drilled throughout the facility, and a bunch of surface faults. All in total, we have about 40 people working out at the lab, 15 USGS employees, and 25 contract employees. Just a plug, if you use data from our stations, notice any issues, have any questions, I'm always happy to hear from folks, and you can email me at the address on the bottom of the slide there. All right, so at ASL, we operate more than 300 permanent seismic stations all around the globe. These include stations in the Global Seismographic Network, the GSN, a number of stations, the US Backbone Network. We've adopted several N4 stations and the IW and NE regional networks in Wyoming, Idaho, and New England. Again, if you have questions or issues to report, we also have maintenance mailing groups for those networks that I've put on the bottom of the slide here. So we cover a number of monitoring missions with the many networks that we operate out of ASL. The GSN is designed to provide global coverage, very high quality long-term observations for both research and monitoring. These stations are installed and operated with a special emphasis on providing really high quality data at long periods. So at periods above about 100 seconds. And providing an even distribution of stations around the globe, or as even as we can get. Other stations that we operate, the ANSS Backbone Network, the N4, and the regional network stations that we've adopted. The goal is a little bit different there. So there, the focus is to support NEIC's mission of being able to monitor magnitude 2.5 earthquakes and greater inside the United States, and to provide fairly uniform coverage across the lower 48 states, filling in gaps between the other regional networks that our other panelists have already discussed, for example. A third mission that we support out of ASL is a portable deployment program. So we have a pool of instrumentation that is held in reserve and can be deployed rapidly in response to significant earthquakes or other seismic events. And the goal there is to get really dense coverage of an earthquake sequence of interest to improve earthquake locations, and to record near source ground motions for hazard studies. I've included examples of each of these stations here on this slide. One recurring theme that has popped up in my 2 years at ASL so far is taking stations that were initially installed temporarily or as part of a portable program and transitioning them to permanent operation. So these are stations that may have been deployed with an initial time frame of 6 months to maybe a year or two in mind. But as they've operated, as seismicity has evolved, these stations have proven very valuable for longer term monitoring. And so eventually, if we find funding and there's support, we can decide to transition a station to permanent operations. And when we do that, the things that I start thinking about are there improvements that we could make in data quality, go out and upgrade the installation, and can we make this reliable if it's going to operate for longer than, say, your expected 1 to 2 years. So a couple examples of that would be transitioning one of our rapid response stations or aftershock stations. These usually consist of instrumentation that's essentially direct buried very shallowly in the ground, a broadband seismometer and an accelerometer with a little portable box to contain all the equipment here. Or alternatively, taking a transportable array station. These were designed to operate initially for 2 years, although many of them have been running for much longer. So this is essentially a tank buried in the ground, sensor at depth, equipment inside, various other instrumentation as well. And then the goal is is to improve reliability. Folks who have adopted other of these N4 stations will tell you that some of these tanks tend to leak. We get flooded instrumentation, which can be a concern. And these aftershock stations with a very shallow burial depth, this is not going to provide you optimal data quality. So one thing that we've been looking into more and more is taking an installation like one of these two types and converting it into a post-hole installation. So this would be taking an auger or a drill, boring a hole into the ground, probably 3 to 10 meters depth, roughly, the deeper the better, and then placing the sensor at depth. And I think I just want to show quickly examples from 2 stations that are probably of interest to folks who study induced seismicity. These are 2 stations that were initially deployed as part of an event response in Oklahoma. So the first station is GSOK051. This is near Pawnee, Oklahoma. So this was deployed in September of 2016. And after operating for 4.5 years, it was clear that having this station in place long-term would be a good thing. It was desirable. So this April, we sent field engineers out to convert it to a post-hole installation. So I have a little cartoon sketch down here. So instead of our very shallowly buried instrument with our box on the surface and our solar panel, we took an auger out, actually managed to get down to 32 feet, which is excellent. It's pretty, very, very augerable clay there, cased with a PVC pipe. And the graphs that I'm showing on the background, for those of you who are not seismologists, aren't seismic network managers, basically we're showing power levels as a function of period. So the lower black line here is sort of the lowest amount of noise we'd expect to see at a really, really good station anywhere on Earth. And the upper black line here is sort of the useful limit of noise at a given station. So, and the yellow lines are showing sort of the range of noise before, from the previous instrumentation before this upgrade, and the rainbow colors show noise after the upgrade. So basically the takeaway message here is that going out, upgrading this this installation, putting in the sweat equity, as Jake mentioned, that this is quite a lot of work for the field engineers, but we get really awesome data quality improvements here. So on the vertical component, we're limited by essentially the performance of the sensor itself. We see a huge improvement on the horizontals. This was already a pretty noisy site at longer periods, but putting it in that post hole has dropped noise considerably by about 10 to 20 dB, which is quite impressive. Another station, same process. We didn't get to auger quite as deep. We only get to 16 feet before we started hitting large rocks. But even at that depth, we still see a considerable improvement in horizontal noise. We put in a slightly higher quality sensor at this location, and now we see excellent performance on the verticals. So this was the upgrade of these two stations was intended to serve as sort of a test bed for improvements we intended to do at a lot of other stations. So we adopted 140 of those N4 stations across the central and eastern US. Long term, I would like to roll out similar upgrades to those stations because, for one thing, purchasing equipment designed to be installed in a post hole tends to be more resistant to the kinds of conditions it can encounter, like getting flooded. And we also see improvements in data quality with these post hole installations compared to the TA style tank vaults. So that's one thing that I see as an improvement for regional monitoring in really most of the central and eastern US. Thanks.
Emily, there's a question. What's the status of the China digital seismic net?
Ooh, it's functioning. I'm not sure what more information the question asker is looking for. Let me see if I can see the chat. Yeah, in general, I would say the CDSN is still up and running. We're still receiving data. If you have a more specific question, feel free to go ahead and ask. Probably an email better, ewolin@usgs.gov, since we're talking about induced seismicity here. Thanks.
Can you see the next question, Emily?
Yes, so there's a question, how does reducing noise improve the quality of the data, or what particular aspect of the data? Good question. So in general, what we're talking about here is reducing the ambient seismic background noise at a station. So basically it means we can pick up smaller signals with that station, right? So you can detect smaller earthquakes. You can get better measurements. So you could produce things like, say, regional moment tensors are one big area of improvement that I'd like to see. If we get lower noise at periods above, say, 10 seconds, then we're able to get higher quality science products out of those stations.
All right, if I would follow up, Emily, thank you for trying to improve some of these stations. But then if I look properly into your network, it seems you only have 4 stations in Kansas. I think you're the only one operating a publicly available network within Kansas. Given that we've had, I think even last week, we had a 3-point-something event in Kansas. Is there any future strategy in terms of putting more stations in Kansas?
Oh, good question. So we do have a few of these rapid response stations in southern Kansas near Hutchinson. There were a few magnitude 4-ish earthquakes there. And we have a strong motion only station in Wichita at the moment in response to some other seismicity there. I do not know of any plans to add additional stations in Kansas, but we have responded to a couple of events there lately so that we can provide publicly available data on those sequences. Okay.
Mitch, within the Kansas, I think Arkansas, the Grand Green Bear, is the sequence still going on? And if we go back, if it's still not going on, do you still continue monitoring the area? And what's the strategy in terms of future earthquakes within Arkansas? I know it's not your primary network, but in terms of monitoring induced seismicity in Arkansas.
No, we've paid much more attention to Arkansas since Guy Greenbrier, of course. And the level of seismicity we detect there now is not discernible above background. So I would not first assume that it's induced. We don't have as many stations there as we did during the 2010, 2011 period, but with the addition of those, we do have 9 stations in Arkansas that weren't there prior to 2010. So overall, we're doing a much better job throughout Arkansas. And Steve Horton and the AGS do have several portables that we move around the state depending on where we think disposal activity will be going on. Just try to keep an eye on things. And it really has not been significant.
Right, talking about strategies and moving stations around. Jake, I see within your map, you have almost earthquakes everywhere. And given that the first networks which came in, I think you and Alexandros, that is Texas and Oklahoma, most of them were ad hoc stations which were getting in where at least you had a big event. Is there, moving forward, is there a strategy in terms of looking into keeping tabs with those, seismogenic faults which had the first events, and what is the strategy going forward in terms of looking at future possible areas with earthquakes?
Yeah, I think the question is related to sort of the fact that the geology doesn't care where the political boundary is drawn. So I think, it's important to understand that some of our algorithms are actually, for sort of the real-time earthquake detection, actually, it's important to stream into our processing systems network data from adjacent states. Even I guess in some circumstances that would include adjacent countries, although we don't go that far south or that far north. But the sort of open data attitude of seismologists sort of actually improves our ability to come up with good reporting out of the actual earthquakes as they're occurring. So that's particularly important. And part of I think the reason for actually coming together in this sort of risk group is the notion that, these things like water disposal or tracking faults that cross state boundaries it's important for us to sort of share notes, share research activities, and try to sort of put our heads together for some of these basin-wide issues when it comes to induced seismicity or seismogenic faults, as you said, Paul.
So,
Paul, can I echo that?
Yep.
We actually import stations from some of Jake's stations and some of Alexandros stations, because otherwise some of those large events in Texas and Oklahoma, our network will mislocate them and make them appear as if they occurred in Arkansas. So adding those stations that are outside of our border helps prevent our systems from making those mistakes.
Yeah, so it's the same for us. I mean, we get data from all adjacent neighboring states, and also we have 10 stations from Mexico, because we have seismicity in the border with Mexico. So that's important for us. I think our work is mostly try to add more stations closer, portable stations closer to the area where we have active rupture zones, because that is actually what is helping, and then also tune the system so it gets better automatic locations that can help actually the analysts to review the events. I have something to add. I like Emily's presentation about the noise level and the idea of moving to postcode. Emily, thanks very much for this. We transitioned 2 of our stations to posthole from 1 meter deployments to one is 100 feet and the other was like 300 feet depth. We haven't seen big differences actually, unfortunately. That's I think that mostly it's because one is in the city of Pecos, which we moved it to 100 meter depth, but this area is very active, a lot of industrial activity. There is an I-20 going through this city, so it's really very difficult. We have seen a small difference in the noise level, very small, mostly in the horizontal components and in a very short frequency band between 10 and 6 hertz. Mostly this band in the horizontal component dropped like 10 dB, the noise level. The vertical component, almost nothing. Probably that's because of the surface waves. We have loose sediments in the area. So it's, I like the idea, I'm very keen of it, I support it. But although I was very keen to do that, the data didn't really help me this time. But it's a good thought. Thanks.
All right, just to follow up, Alexandra, I think you mentioned at some point that you also have some data set contributed by the industry. Is that data available for the public or it's not?
We have two types of data. One that follows the incentive with the regulator. So the regulator has posted an incentive. So if one operator would like to increase the volume of injection, then this operator should deploy a seismic station and make the data available to TextNet. And then we have the data, and then of course we provide this data to the public as well. So that is one case. And we have a few cases where we have NDAs signed with the operators. If they have private arrays, they share the waveform data with us. We are not allowed to share the waveform data with the public, but we share the peaks with the public. So if you download the QuakeML file from USGS, for example, or from our FDSN web services, you can get the peaks, the station locations, but you will not have access to those, to the waveform data of those stations.
All right, thank you. So looking at Jack's map, you had earthquakes, and even Alexandros, you had maps, earthquakes across the borders. How much of coordination do you do as individuals in terms of figuring who within your region should be reporting some of those earthquakes?
I call Jake.
Yeah.
Or she calls me. Yeah, that's the easiest way.
Well, there's I think, yeah, just sort of open lines of communication is important, but also, you know, we have some post-processing that, I mean, not like post-processing, like we push any buttons, but before we report out to USGS, we have some checks that don't always work, but that should just report earthquakes within our polygon. And so I sort of alluded to some mislocated events. You know, there was one we sort of reported out into Arkansas, which was an issue of one of these regional kind of earthquakes, or one of these very small earthquakes in our network that looked like it was a regional event. So mistakes do happen. We have a delete button, so we can delete, you know, earthquakes and that sort of reporting. But we're pretty good at getting the largest and most societally relevant earthquake information out as quickly as possible within seconds.
Thanks. So we have a question from from Lisa Block. He's asking, with the increased number of seismic stations and as the increased rate of earthquakes being detected, how much work has been done in recent years in improving the velocity models used to locate these earthquakes?
Okay, let me start.
Paul, you can probably answer that. Although you're technically right now you're a moderator, but we are at OGS. We are working on exploring whether you know, tomography derived from earthquake from the earthquakes can actually be utilized. So if you come up with a 3D model for the subsurface, can you actually utilize that in a sort of production environment? So that's kind of a sort of research question that blends both sort of the research activities and sort of our role as sort of an observatory. But so look for future work coming out from Paul on that.
Alexandros, take over, answer.
So for our case, we use a general model for the whole state, except from the area of the Delaware Basin. We have a local 1D Earth model that is derived out of the tomography that we did pursue during the first couple of years of the data we acquired through the network. So that is what we currently use, and there is a plan to upgrade this model somehow, especially for the Permian Basin, because we see that the model affects very much the depth, as expected, of course. but it is important for making for decision-making processes that the regulator or the industry is trying to follow.
So Mitch, with the velocity model, do you have a varied velocity applied across your larger region, or it's just one?
No, we use different models depending on where they are. There's about 6 different velocity models we use depending on where it is. We have the system configured to be able to do that. We don't use a 3D model for the whole region, but it's quasi, it's really 1D with many different models. We haven't made any adjustments to those models recently, but the additional data really goes into doing the research and getting the 3D tomography that helps understand the sources and the causes of the intraplate seismicity. So that's where it really benefits. Once you get a close station, the better models have a better improvement on the depth of the earthquake, of course. And once you get a close-in station, having a decent model is as important as having a close-in station.
Thank you. So I think this is a little bit out of the realm of maybe seismicity, but Jack, I think this is a question for you from Jeremy asking about the Abaco injection where that data is available publicly.
Yeah, the data is available on the OCC website, the Oklahoma Corporation Commission website.
Okay. Going back to Mitch, there's a question from Seth Carpenter. He's asking whether CERI has made any progress towards earthquake early warning. You know?
No, in fact, we're told the USGS that we shouldn't, not with their money anyway, because they're focusing their EEW money on the West Coast. I don't mean to be that. So no, we have not, and there are a lot of issues there that would require some significant funding that's standing in the way. The data latency at the station, the software and the processing and the redundant hardware. So going to EEW is a much bigger operational challenge than running a routine, a traditional seismic network.
Okay.
All it takes is time and money, Seth.
Yes, of course. So yeah, so Mitch, I think from your side, so you had a lot of contribution in terms of your geographical area with the number of networks within your area. Alexandros, I remember at some point there are some institutions within Texas, like SMU had some networks. Do they still have that information being given to you, or it's no longer there? Especially within the DFW area.
Yeah, in the DFW area, there are some stations that have been initially deployed by SMU that are funded by TextNet, and these data are available to the public through IRIS, and we use it also ourselves on our earthquake location. And we have complemented this network with TextNet somehow stations that we deployed back in 2016.
Okay. Right. Coming back to Emily, I think I'm one of the beneficiaries of one of the oldest network stations. I think WMOK. Question is, going to some of these stations, do you have any strategy, or do you have any plans for maybe putting more advanced station? I mean, sensors to some of these old stations?
Oh, it's a good question. Yeah. You asked about WMOK in particular. We need to get that one back online.
Typically, he's asking about that station.
Of course. Yeah, it's been down for a while. We're getting slammed by COVID travel restrictions. It's unfortunate to be in Albuquerque when most of your 200 stations are, sort of Mississippi, east of the Mississippi. WMOK is, of course, much closer. Yeah, I think I always sort of am looking for stations that could be upgraded if we end up having a little bit of extra funding, putting a borehole in or something. WMOK might be a good candidate since there is hard rock that's easy to get to from the site. So yeah, it's always in the back of my mind. I think trying to improve the reliability and data quality of N4 stations is sort of the major item on my list at the moment. We adopted those stations in 2019, and a lot of them need a lot more work just to get them up to snuff before we start upgrading. But I'm always thinking about stations where we might be able to advance. We've had some cool advances in station installations on the GSN side of things. So even doing like a pier drilling technique, taking a drill and just getting 6 feet or so down into hard material has done some really cool, has produced some cool noise improvements. We have the STS6 sensor now that has a very low noise floor. So yeah, there's a few options we might have if the opportunity presents itself.
Okay, so let me check more questions here. So Dina, do we have any more questions from the YouTube? I can ask.
No questions at this time.
Okay. So going back to Mitch, I think you have one more question from Seth. Are there any benefits to analog telemetry of the digital?
Oh, absolutely. The dynamic range for the digital telemetry is at least a couple of order of magnitudes greater than the analog telemetry. So you don't clip as quickly.
Okay. So
the analog telemetry, though, is a whole lot more bulletproof, though.
It's been used for more years.
Yeah, and the path problems are much more forgiving with the lower frequencies of the analog telemetry. So there's a lot of good reasons to have it, but the limitations of the dynamic range, clipping for larger earthquakes really detracts from our ability to do analysis on the earthquakes for the larger events. And so the converting everything to digital is fairly important. Plus, it's harder, it's getting increasingly difficult to get analog hardware these days.
Okay. Alexandros, so you talked about some seismicity occurring across the border. I know the basin doesn't stop when you're in New Mexico or within Texas. So are you the one who reports the earthquakes across that basin on the?
The agreement we have with New Mexico and Maryland and the USGS is that we report up to 10 kilometers inside New Mexico from the state border. And that we provide it to our website, and also we send it to USGS. I hope that New Mexico and Mary will soon can be authoritative so that they will have their own polygon based on the state boundary, so they can provide directly to USGS the seismicity. But certainly we have interest about the seismicity in the border because, as you said earlier, earthquakes doesn't have state borders or country borders. So it is of our interest to see how the earthquakes migrate to the south.
Okay. So I think maybe something we may have missed during the introduction. Jack, where do you think the network is going, and what is in terms of strategies, and what are the limitations you think you may be foreseeing?
Well, I mean, I think that's a unique answer for every network. Our particular issues are funding, of course, just keeping the lights on and maintaining a sustainable network, while also trying to serve the interests of the public. We like I shared, earthquakes are occurring all across the state, and the citizens want timely reporting of those events, especially the felt ones, and obviously we can't report as well or down to lower and lower magnitudes everywhere in the state in a timely manner. It's just a function of aging equipment that isn't being recapitalized upon. We have some proposals in front of the state to hopefully fix that issue, but that obviously changes with the shifting winds of those kinds of climates. So we're hopeful that we'll have some opportunities to get some federal investment through DOE or USGS in the future to help support the regional monitoring, because I think what Oklahoman demonstrated over the last decade is when you put stuff into the ground, it becomes a regional issue very, very fast, especially when the economics are in favor of, hydrocarbon extraction. But in the future, we might think about putting fluids back into the ground for large scale, regional carbon storage programs. And so just reminding, leaders that those things cost money. So you want a reliable seismic network, do some substantial planning ahead of time, budget out for several years, and then you can actually maybe more safely realize some of these broader, regional kind of scale projects.
Okay, thank you. So we're almost towards the end, but I think Sean Maxwell has a question here. What are the efforts which are being made try and measure ground motion, specifically related to the small magnitude felt events within the region? So maybe Jake, you could just take over from the Oklahoma side, and
that's a very very broad brush there. Thanks for the question, Sean. But yeah, so we've identified some interesting, very small footprint, but very strong ground motions that are sort of higher than expected for the magnitudes of some of the events that we observe, especially around well completions. And obviously, you want, in those cases, it would be great to get instrumental recordings near those events. Obviously, we can't forecast exactly where those are going to happen. So it becomes sort of, one of these resource questions about, you have a finite number of resources as a public entity, and we're charged with observing seismicity across the state. So we can't really do those small scale, pilot studies. In some circumstances, we have had success at getting industry data sets, but it would be good to, envision a future where there's a forum where there can be a freer exchange of that type of, crucial information. And I think that there's receptive ears out there in that world that operates in the sort of public-private spaces, and I think probably some of my colleagues have had more success with that, but I'm just hopeful for more of those types of opportunities.
Yeah, I can chime in on that as well. I think so there's sort of two things I want to say in response to the question. One of them is for recording ground motions from smaller magnitude events. I think that's part of the reason why we've had support for leaving some of our rapid response equipment out for much longer than typically anticipated, say 2 years or more. Most of the time we're looking at a 6-month to 1 year deployment. So that goes for Oklahoma for, say, induced seismicity, but just in general, we've left instruments out in Ridgecrest and Puerto Rico in response to events there. Those events are, those areas are mostly having magnitude 2 or 3 aftershocks at the moment. But we do still have some equipment out there that can record smaller magnitude ground motions. And then a project that I've been involved, not as a primary participant in, but I've contributed a little bit to the folks that run Shake Map up in Golden. They've been developing code to called GM Process. It's in the process of getting released and published. But one object of that is to be able to include ground motion measurements from broadband seismometers, so detecting clipping, doing data QC, but basically being able to ingest data from a wider range of sources, including for smaller magnitude events, so that we have more ground motion information from sort of magnitude 4 less events.
Okay, thank you. I think we are running out of time, so I think Lily probably will kick me off and take over.
Yeah, some closing remarks. First, thank you, Paul, for spearheading this panel. And thank you, panelists, Jake, Mitch, Emily, and Alexandros, for participating in a very engaging discussion. And before we take off, I want to gratefully acknowledge the US DOE, the National Energy Technology Laboratory, and the Groundwater Protection Council for funding this webinar series, as well as the research conducted within our collaborative. The next webinar will be in a more traditional format and will take place on December 7th. And for this webinar, we will have the joint presentation between Dino Wong at the Bureau of Economic Geology at UT Austin and Mary Litherland from the New Mexico Bureau of Geology and Mineral Resources at New Mexico Tech. And their presentation will cover the results of a Texas-New Mexico interstate research project, which focuses on assessing earthquake hazards in the Northern Delaware Basin. And with that, thanks again. Take care, everyone.
Thank you.
Thank you.
Bye-bye.
Thank you.